The theory we're going to use primarily, and especially in this chapter, for acids and bases is called the Bronsted-Lowry theory. And in the Bronsted-Lowry theory, or just Bronsted theory as it sometimes is called, an acid is a compound that donates a proton, an H+, to another compound. And a base is a compound that accepts that proton from another compound. And there's lots of examples of Bronsted acid-base theory around us.
Ammonia acts as a base in solution by accepting a proton from a water molecule. This liberates a hydroxide ion and results in a basic solution.
This is a reaction between ammonia, NH3, which is actually basic, as we talked about back in Chem 221, and NH3, a base, reacts with water, H2O, to make ammonium, NH4+, and remember ammonia and ammonium are different, and hydroxide. But what I'd like you to look at in this particular reaction is how water here is donating an H+. Like on the product side, water becomes hydroxide, which is water without the H+. So the H+ is donated to the NH3. That makes water an acid. But if NH3 is accepting that H+, that means that NH3 is a base. So on the product side then, NH3 becomes ammonium, which is NH3 plus an H+, and you're good to go. However, notice that this reaction has equilibrium arrows, the double-sided arrows we talked about in the last section. And like all equilibrium, you can think about them as reactants going to products as well as products going to reactants. So now let's consider ammonium reacting with hydroxide. And if you think about it from that perspective, the ammonium is donating an H+ to the OH-, so ammonium becomes ammonia. So ammonium is an acid, and the hydroxide here is accepting that H+ from the ammonium to make water, so hydroxide here is a base. So when it comes to equilibria, you can have acids and bases on both sides of the reaction, and that's going to be one of the things we talk about in this section. So in this reaction, ammonia is a base and water is acting as an acid. And the ammonia makes ammonium, which is an acid, and the water makes hydroxide with the base. So notice that a base makes an acid on the other side, and an acid makes a base on the other side. The NH3, NH4+ combination is called a conjugate pair. And a conjugate pair is just two chemical species which are related by the loss or the gain of an H+. So you add H+ to ammonia, you get ammonium. You take an H+ away from ammonium, you get NH3 ammonia. So they go back and forth. The other conjugate pair in this equation, of course, would be water and hydroxide. You give up an H+ from water, you make hydroxide. Hydroxide gets an H+ and it makes water. So we have two conjugate pairs in this reaction. Ammonia, the base, and ammonium, the acid, as well as water, the acid, and hydroxide, the base. This is another reaction of an acid-base reaction. This is hydrogen carbonate, HCO3-1, and it's acting as an acid here because HCO3- is giving up an H+ to become carbonate, CO3-2-. So notice that carbonate and hydrogen carbonate are conjugates. HCO3- is the acid. It has more H+, so it gives up the H+ to the base, which accepts it, CO3-2-. But water is also making its own conjugate pair. Water here is acting as a base. It's accepting the H+ to make hydronium, H3O+, an acid. And you can think about it, of course, as hydronium, the acid, giving up an H+ going to a base. So a couple of things here. Conjugates are really important. Conjugates are just two chemical species where you're either adding or subtracting an H+ to give the other one. One of them will be an acid, the one with more hydrogens. The one will be the base, the one without less hydrogens. Also notice here that water is acting both as an acid in the first example with ammonia, as well as a base here in hydrogen carbonate. So water is an example of a compound that can be both an acid and a base. It just depends on what else is around it. So this is a question you might see. It says, which of the following is not an acid-base conjugate pair? And the punchline here is that conjugates are related by an H+, plus or minus. You add the H+ to the base and it makes the acid. Take away the H+ from the acid and it makes the base. And hopefully you can see right away that it's answer A, which is not a conjugate, because HClO has a hydrogen, chlorine, and an oxygen. And its conjugate is not going to be just chlorine fluoride, because conjugates are related by H+. So the conjugate of HClO would be ClO minus 1, and the conjugate of Cl minus would be HCl. Those are how conjugates work, so it wouldn't be the other one. But if you look at B through E, they're all plus or minus and H+. So HF there on B, take away the H+, it becomes F minus plus an H plus becomes HF, you're good to go. The last one there, E, HNO3, take away an H+, you make nitrate, NO3 minus 1, add an H+ to nitrate, you make nitric acid.